Oh, I had to move the camera to do the recordings for the conference, and now everything's messed up. I'm not gonna lie to you guys, this is number 3. It's been a hell of a few weeks. So, hey there, drinking buddies. Welcome to Scientific Drinking. We're going to be doing something a little bit different this time. The past few weeks, I've pretty much been gone, not on social media, not making any videos, not doing anything. And that's pretty much been because I've had to knock out a couple of papers. And to be honest, biting off 2 papers for one conference has been a little bit regrettable. But I made it through, and I think I got a couple pretty good papers. So what we're going to do in this episode is I'm going to pretty much summarize the work I've been doing with papers in kind of layman's terms for people who aren't in this field and have no reason to know all these details. As they say, if you can't explain something simply, well, you don't understand it well enough. So let's hope that I can explain it simply because I'm publishing in it, right? So in this episode, we're going to be talking about how spacecraft navigate. I mean, that's right, like actual rocket science. So here we go, Rocket Science 101. Cheers. So tonight I'm drinking Orange Blossom Brewing Company's porter with coconut added. I think it's TCP. There you go. It's a pretty light porter. I don't like my porters too heavy. So first, credit where credit's due. I could not have knocked out these papers without the help of some really good mentors and some dedicated coworkers. So for the work we're beginning to talk about today, special thanks to people at Embry-Riddle and Torino Polytechnic University, such as Gennaro and Elisa Capello. You guys have been great. It's been good working with you. And of course to my mentor, Murad Nazari. Been very patient with me as I learn these things pretty much from scratch. So here we go. So let's talk about what does it take to control a spacecraft? Well, there's a lot that goes into that question, as you might imagine. But for now, we're going to talk about 2 key parts. One is the position of the spacecraft, X, Y, and Z, where it is in physical 3-dimensional space, and also where it's looking, its attitude, where it's pointing. Physically, in terms of sensors and equipment, there's been a lot of different tools used over time. And things are more complicated in space than generally they are here on the ground. For things like your smartphone, you have GPS and a trio of magnetic sensors that always determine where you are and where you're pointing. And we take that ability to know where we're at and where we're looking at all times as kind of, we take it for granted, right? It's super easy. All cell phones have it. But of course, it wasn't always that way, and most of us probably remember days when we didn't have that kind of convenience. So in order to provide a GPS signal, satellites need to be placed in a geostationary orbit. And GPS satellites don't rely on GPS to get to geostationary orbit because, well, that would be circular. So before we had GPS, we needed to control our rockets before we even made it to space. Some of the earlier rockets, like the German V2, relied on an internal guidance system to navigate it to its orbit. And this isn't as complicated as you might be imagining it is. It pretty much came down to balanced springs tied to throttle cables. Just a cable with a spring. It depended on the amount of acceleration given, it depended on how much force was put on the throttle in a given direction. These were called PIGA accelerometers. The other tool on board these early rockets was a couple of gyroscopes. So those gyroscopes would spin up very fast. They resisted any change to their pitch and attitude. That way the rocket could tell which way it was pointing based on where the gyroscopes were pitching because they maintained the same direction as they did when they were first spun up. So they had 2 gyroscopes, one for pitch and the other one for roll and yaw. This came with a pretty big disadvantage. Both of these were completely internal guidance systems, which mean they couldn't be modified after the thing was launched. There's no radio input. You couldn't remote control these rockets. Once they were gone, they were gone. And so V2 rockets were notoriously inaccurate. The best use was for terrorizing people rather than actually hitting useful targets, which is why the Battle of Britain lasted so long and why they still need to send airplanes. As we got better at using rockets and developing computer technology, we were able to incorporate things like radio transceivers onto our rockets and spacecraft. That allowed things like the Voyager 1 and 2 to receive small adjustments and control signals as they made their way throughout the solar system. More recent technologies include sun tracking and star tracking sensors, which enable spacecraft to determine which way they're pointing based on how the stars are configured in any given position in the sky. Pretty cool stuff, right? But physical mechanisms are only part of the problem. In fact, they're the easiest part. Some of the more difficult parts is the formulation, the math. And I know how I feel. I try not to get too much into math in the show because, people tend to fade out.
I've no more fucks to give. My fucks have runneth dry.
I don't blame you. Some of this math can get kind of grueling. So I'm going to try to keep that to a minimum, but talk at a higher, more conceptual level. You see, control theory for spacecraft, really the idea and the math that goes behind controlling something, is notoriously difficult to read and interact with. There's so many notation. There are superscripts, subscripts, wedge matrices, skew matrices, unwedge operations, adjoint operations, bars, tildes, and that's only the stuff I'm familiar with. Back in the day, there was this guy called Leonard Euler. And if you've been in math and physics for more than a couple years, you would have heard of him. His name's everywhere. Euler's equations, Euler's methods, Euler's formulas. The guy was brilliant. His name is everywhere in physics and mathematics, and his accomplishments include breakthroughs in geometry, group theory, graph theory, number theory, kinematics, number integration, the motion and behavior of planets, logic, and even math. Honestly, this guy deserves his own episode, and maybe one day I'll be able to get to that. The list just keeps growing, doesn't it? But there's one thing that he did that isn't perfect. Far from it, in fact. Euler angle. This is pretty much the most basic element of control. It has 3 degrees based on which way you're pointing. So if I'm sitting here now and I turn 90 degrees to the right, I've adjusted my yaw by 90 degrees. If I lay down and looked up, I'd be adjusting my pitch by positive 90 degrees. And if I rolled like this, then I would be adjusting my roll by 90 degrees. So these are basically the 3 Euler angles, describing which way you're looking. However, there's a small problem here. You see, the sine of 0 is the sine of pi. They're the same. So it has these problems called singularities. When you look in the opposite direction, the spacecraft doesn't really know which way you're looking, and that's kind of a problem. So enter quaternions. So quaternions basically adds another variable that soaks up that uncertainty. You can't reach a singularity with a quaternion. But it's redundant and it's non-unique, meaning that there's more than one way to reach a certain place, and there's an extra variable which kind of slows things down. That's where rotation matrices come in, and that's where SE3 comes in, which is the formulation I've been working with. So a rotation matrices actually has 9 variables in it, and it's a 3x3 matrix. If you're familiar with matrices, I remember I used to hate matrix operations, but don't worry, we're not multiplying anything together here. Basically, it doesn't have any of the other disadvantages aside from redundancy. Yeah, there's many other elements, but it doesn't have non-uniqueness. It doesn't have singularities. And as a bonus, it can be used in a compact form. And what I mean by that is if you put your position vector with your rotation matrices and slapped them together in a 4x4 matrix with a 1 in the bottom right, you'd have SE3's basic form. All the schemes I've mentioned until now were only attitude dynamics, basically in what direction your spacecraft was pointing. But there's also the dynamics part that's conceptually easy to understand, where you are in 3-dimensional space. Are you on the 3rd floor? What part of the 3rd floor? 3rd floor corner office or 3rd floor center office? Your X, Y, and Z position in space. But in certain situations, just treating these separately isn't really doing the situation justice and can be quite inaccurate. For example, if you're in the presence of a strong solar wind, or maybe you're orbiting a small lopsided asteroid like Itokawa, Pan, or Bennu, well, then the way your spacecraft is pointing has an effect on how your spacecraft moves. So, in other words, your pointing direction and your translational direction are coupled. They're tied together intimately. You can't really separate them and still have an accurate system. SE3 is the Mac Daddy of dynamics, if you have the time and patience to wrap your head around it. The initial formulation seems simple. You have the rotation matrices, the row vector, and a 1 in the bottom right. Calculating this together makes things go pretty fast, actually, especially for computers that are used to calculating 2 things at a time. Now it's just one formulation. But if you're doing it by hand, well, I told you I wouldn't do any matrix operations, and I'm going to stick to that. You can imagine this is going to get kind of complicated. The challenge arises when trying to conceptualize what's going on with your spacecraft in your head, especially when you have some of the more complicated formulations. You have a control system. You have to trace where each variable goes through, especially when troubleshooting, and this can be time-consuming and difficult to understand. So that's basically where the formulation is right now. We've defined it, we've run it through a few of its paces. It's proven itself to be very robust, very fast, and very accurate. Unfortunately, it's hard to think about. It's not intuitive at all. And so we have to develop a whole new way of dealing with this kind of SE3 algebra. And recently, many people have succeeded in building quadcopters and robots and testing their math on those little devices, and it's worked great. And I'm in the process of trying to develop it for spacecraft. And maybe one day soon we can put it on board a few of these guys that I have in mind. But we'll save that for the future. So some of the challenges facing rocket science, especially when you have a spacecraft that's far away, is you can't always rely on the sensors. Remember all those sensors we talked about earlier? Well, they're not perfect. Far from it, actually. They can be kind of noisy, especially when the sensor input isn't always that great. You have noise from the sensors and you have noise from the onboard computer, which is constantly bombarded with radiation in space. So usually you have something called a filter, which averages all this noise out. And that sounds simple enough, but when you're dealing with new formulation like SE3, it can get kind of counterintuitive and it's difficult to work with. Like I mentioned, the people with the quadcopters and the robots have made some progress recently and in developing some new schemes for adding filters to SE3. The next challenge is adapting a controller, something to control a spacecraft despite being noisy. You know, all these sensors and all these instruments aren't reading exactly what's going on. And you have to control your spacecraft even though you're not getting perfect information. It's kind of like wandering through the world wearing someone else's glasses. Everything's a little bit blurry. The information you're getting back isn't always accurate. But you can usually average out all the blurry motion and make your way down your front porch and down the sidewalk. That blur is the process noise, while you making your way along the sidewalk, even though it's not perfectly defined, that's the controller. Spacecraft need a controller too, especially when they're so far away that a human operator can't correct for all that noise and inaccuracy. Now let's give some real context. This is Saturn's moon, Pan. Looks like a ravioli or maybe a UFO. It orbits inside the rings of Saturn and is actively accreting new material from the rings. In other words, forming as we watch. Its interesting shape and low gravity mean that orbiting it is no simple thing. And even if you ignored all that ring material flying around, this is one of those scenarios where I mentioned that your position and attitude are coupled. And it's a perfect test for our notional simulated spacecraft using this new SE3 formulation. And so that's what we did. We tried to maximize coverage over the asteroid so that we could map the entire surface of our simulated mission to Pan. And it worked great. The next test we used Bennu. You might have heard about Bennu before. Bennu is pretty well known as that object visited by OSIRIS-REx on the first sample return mission to an asteroid by the United States. It's a near-Earth object, or NEO, and there's about a 1 in 2,700 chance that Bennu will impact the Earth sometime in 2060. So we sent a probe there and we want to know what we were dealing with. Turns out it's kind of a pile of rubble, half a kilometer in diameter. Not really spherical, but it has very, very low gravity. I mean, we're talking about 6 micro-Gs or 6 millionths of a G. So it's kind of tricky to orbit. And it's another good test of our controller because it's not really spherical and it's any little inaccurate burst of thrust can send you pretty much into escape velocity. Finally, we took a look at Itokawa, a very irregular peanut-shaped asteroid once visited by a Japanese spacecraft Hayabusa in 2005, bringing back a sample of 1,500 dust particles for study. This, too, is an NEO with a possibility of intersecting Earth. It's no coincidence that we visited 2 of these asteroids with possible collision chances with Earth, not only because we're interested in what's going to be slapping us in the face. Orbits that are very similar to Earth's are very easy to reach. So if you've ever been sitting there sipping a beer at your nice favorite pub, wondering what's the state of the art for spacecraft control and navigation, well, now you know. For me, there's still some work to do with this SE3 formulation. I'd like to add an optimization routine into there to make it possible for us to optimize trajectories in this formulation, which has never been done before, at least not to my knowledge. And of course, there's a lot of work to do with making the model more accurate and adding a more robust controller. And we don't really have a guidance scheme, kind of a navigation, but guidance, which I know they kind of sound like the same thing, but they're different. They're a little bit different. So we need to add more robust logic and make it, be able to take care of itself a little better because what we've done is pretty basic.
Yeah, you basic.
But all journeys start with a small first step. So thanks for watching. I'll see you next week when we talk about electrified dust in the lunar environment, which was my other paper and completely unrelated. Cheers.